This is process model, and this is the event log where it originated from. The goal of this video will be to explain how we went from the event log to the model. You will have a mental image of how the inductive miner exactly works.
So let's say we start with what we call a directly follows graph, so a DFG. The way it would work for a DFG is that you have your A, you have B, you have here we will have C, let's say here we have D. I will ignore for a moment the relationship between the direct relationship between B and C because that's the core of our argument here. And the goal from this exercise is that I want to be able to count how many times each of these letters it's following the other letter. So B follows A 3 times, so that's 3 times. C follows A 2 times. D follows B 2 times, so that's 2 times. And D follows C, if I'm not wrong, 3 times. Same thing would go for E. I don't need to sketch it here. The question comes to when here there is a relationship between B and C, because C follows from B 3 times, and then B follows from C. Here we have 2 times. So here the question is this a loop, or if we had our DFG diagram, is this a loop? The answer is not. It's not a loop. It is actually what we call concurrency. And that's something that gets solved by our inductive miner. We will see how we do that in the video, of course. So here I finished building the E for our DFG. Now, to show you how the inductive miner works. So the inductive miner is a recursive algorithm, meaning that we have a sequence of conditions, and at each step we're gonna check that a certain condition is fulfilled or not. So first of all, I'm here. I'm gonna build the set of elements that are present in our trace. So A, B, C, D, E. That's very simple. So it's all the elements that are present. It's the set of all the elements that are present in our trace. And these are the conditions of our algorithm. I will not read them for you right now. I'll just show you how to start and you will get it. First of all, we have the sequence. So the sequence says in every trace all activities from subset 1 appear before all activities from subset 2. So let's say we create 2 subsets from our trace. So we look here in our trace and we need to create 2 subsets that elements from subset 1 always appear before the elements of subset 2. The answer here is already in the definition and it's already very clear. It's A. So let's say we put A in its own subset here, and we have the second subset B, C, D, and E. This is a C. So this means that we have a sequence. That's the first condition already fulfilled, so no need to check the other conditions. I need to delete this. Okay, this is deleted. From here, it means that we have an A and the sequence to the other elements. So we delete this. So after that is fulfilled, what we do is that we delete the first element. So A, we already have the relationship for A. What's still for us is BCDE. So for BCDE, we're gonna, as always, ask the first question. Which subset either comes always, we create 2 subsets and the elements in one subset always come before or after the elements of the other subset. So here, as D is always, as you can see here, D is always coming at the end. It means that the elements from B, C, C, E are always, we have a sequence between them and the element D. This means also that D is at the end of our model. So the same thing as A, we come here, we eliminate D, and we delete. I shouldn't have deleted the BCE, but here, for completeness, so B, C, E. So for BCE, as you can see, sometimes E comes before BCE, and so for sequence, that's not going to be feasible. So sequence is not included. Now we think about the exclusive choice. Exclusive choice, it says in every trace, activities from only one subset appear, never both. So one subset always appear one of the two subsets. So here, as we can go back to our trace, either we have E or BC in the same trace, meaning that what we are doing here is actually we have two subsets, BC and E, and we have in the middle of them an XOR relationship. So that is explained. Now what I will do is that I will delete E, and here back to BC. So I'll go here, I will delete this one again. Now it's very easy, you know the sequence. Now for BC, we have BC. First of all, we check for sequence. It's wrong, of course, because sometimes, as we can see here, sometimes C comes before B and sometimes B comes before C. So it's not sequence. Second one, exclusive choice. B and C come at the same time almost always. So meaning that it's not the second one, it's not an exclusive choice. So it's not here. So it's not the second element. Now the third, parallel. It says in every trace, activities from both subsets appear, but their relative ordering varies across traces. So sometimes subset 1's activities come first, sometimes subset 2. Both must happen, order is free. So as we can see, C and B appear in varying orders, and here we have a parallel relationship. So I'm gonna do this, I'm gonna delete, and that's a parallel relationship, or actually you can display it with a +2. And here C. So now we delete what we already have drawn, and we do the reconstruction of our tree. So step by step, here when you do your tree, you're always executing or building your model with the left child before the right child. So we started with A, and here we had a sequence, then we go from there, and D, then if I'm not wrong, we had a choice, an XOR, go down. From here we had either E, or here we have a parallel. In the parallel we have B and C, of course. So what's nice about the inductive minor is that it guarantees soundness by construction. Soundness by construction. So this is a concept that I will explain in other videos, because it introduces deadlocks, Petri nets, and a lot of notations and concepts, but it's easy. And we will see that in other videos, of course. So this is our final result. So we have our tree, and when we go here, we can see our model. Step by step reconstructing from the left child. First of all, with the sequence, then we have the XOR, then we have the parallel or the execution of the E, always dealing with the left child before the right child. One more thing we discussed already before is that we thought here, if we followed our DFG, that we thought that we had a loop, while in reality we had a concurrency, a parallel relationship. So with the inductive minor, we avoid this confusion. So, and this is again our final result. So if you liked the content, please like and subscribe and follow me on LinkedIn. Thank you.